Welcome to the 18th lecture for the NPTEL course on computer system optimization for machine learning. As usual, we will give you a brief recap and then we will continue on DNN pruning. So, in the last class we discussed about unstructured and structured pruning. So, we saw that different advantages and disadvantages of unstructured as well as structured pruning. In general, it is favorable to do structured pruning, but because it is more beneficial to do so in from the hardware performance perspective. Now, let us continue the discussion on DNN pruning. So, let us say we are performing the magnitude based pruning. Okay. So, let us assume that this particular figure is showing the distribution of the absolute value of the weights. So, as you can see that lots of weight has the absolute value near 0, correct. Now, let us say we have devised a pruning technique that we have in there we removed the weights which has near 0 absolute value, right. Now, it is seen that if we do so, maybe till 50% of the pruning ratio, the accuracy is same. The accuracy is same as the unpruned network. Here the black dotted line is showing the loss for unpruned network, and then this purple line is showing the loss for pruned network. Okay. So, as you can see, so when we have 50% pruned network, then the accuracy or the accuracy loss is almost 0, right. This is the 0 line. But after pruning more than 50% of the network, the accuracy drops drastically, and then when we have like 80% pruned network, the accuracy drop is like 4.5%, which is huge, right. Now, what we can do is, the question is, can we recover the lost accuracy performance? Means we want to prune more, than 50% of the network, but without sacrificing on the accuracy front. One can do fine tuning. When we say fine tuning, that means maybe after pruning we can train the few like last layers, maybe last 2-3 layers. So, one can train last 2-3 layers, that is the fine tuning. So, after fine tuning we may see this kind of multimodal distribution. So, this is like pruning without fine tuning, and this is with fine tuning. This is pruning, just pruning, and this is pruning plus fine tuning. So, as you can see that if we do fine tuning, then maybe the number of weights whose absolute value is 0 is less, but those are not completely removed, right. In this case those weights are completely removed. Now, as a result of fine tuning, you can see that again this is the accuracy of fine tuned model. As a result of pruning plus fine tuning, you can see that we can now sustain approximately 80% of pruning. So, till 80% of the pruning there is no accuracy loss, but then after 80% of the pruning there is like significant accuracy loss. The loss is increasing drastically, right. Now, on top of fine tuning, we can do this process iteratively. So, we can perform pruning, then fine tuning, and then again we can perform pruning on the fine tuned network. After that again we can perform fine tuning. So, that is the iterative pruning and fine tuning process. If we do that, then you can see that we can probably sustain like 90% of pruning. So, with pruning, this is iterative pruning and pruning plus fine tuning. Okay. Now, as you can see that if we do not do any pruning, if we just do pruning, no optimization after pruning, then we can only survive 50% of the pruned network, or we can get only 50% pruned network without any loss in accuracy. If we perform fine tuning, then we will be able to prune 80% of the network without any loss in the accuracy. If we perform this activities in iterative fashion, iterative pruning and fine tuning will provide 90% pruned network without any loss in accuracy, right. So, that means you can see that we can develop new technique which can recover the lost accuracy after pruning, right, and we will discuss more of these techniques. Again, in the last class we briefly touched upon the topic about which parameters to prune. This is one technique is derivative based pruning. So, you can estimate the importance of a neuron by the error induced when removing that particular neuron. So, let us say we have like 1000 neurons in a network. What I mean, one can actually remove 1000 weight or remove weights one by one, and then see what is the importance of the neuron by the error induced when removing that neuron. Let us say I remove the 50th weight, and then I can see what is the accuracy. After that I remove, I mean we after that maybe I can put that 50th weight back, and then I remove 51st weight, and then I can see what's the effect on accuracy. So, by this technique we can estimate the importance of a neuron by the error induced when removing that neuron. But again, removing each neuron and calculating the error is computationally expensive, right. If we have, let us say, millions of weights, then we have to do millions of iteration to obtain the importance of each neuron, which is, I mean, which is huge. And again, remember, I mean, it's not like removing more than one weight. So, we are just removing one weight and then putting it back. We are removing one weight, see the change in accuracy, and then putting it back. Then we remove the next weight, see the change in accuracy, and then put it back. So, that is how, I mean, if we really want to assign importance to each weight in this fashion, then it will take lot of iterations, which is like very computationally intensive. Now, instead we can use Taylor series expansion to approximate the importance. Now, by that what I mean is, we can perform a perturbation delta u of the parameter vector that will change the objective function by this. So, I mean, let us say u is one of the weight. So, if u is one of the weight, we can see what is the change in error or change in accuracy if you change the u by delta u. Okay. So, if we do that, then we can express this delta E as this particular expression, where it is saying delta E equals to summation of I g I multiplied by delta u I, then half of summation h I I delta u I square plus half of summation h I j delta u I delta u j, and then order of delta u to the power 3. So, if you look closely, this is nothing but the gradient, or this is nothing but the change in error if we change our weight by delta u. Okay. So, you can think that this is like delta E over delta u, this is delta E over delta u, you can think like that. Okay. I mean, delta E over delta u is something, and then if we do delta E, then it will be delta E multiplied by delta E is equal to x multiplied by delta u. Now, here in this particular expression we have different terms. So, g I is nothing but delta E delta u I, and then h I I is I mean, or in general h I j is the second order derivative, which is delta 2 E delta u I delta u j. That means, if I change the ith weight by delta u I and change jth weight by delta u j, then what is the change in the error, right. And then finally, we have this term which is the third order term or more than second order term, right. Now, with in that expression we can make some assumptions. The following assumptions can be made to simplify the expression. One is the diagonal term, the change in error caused by deleting one filter is independent of others. So, that is why we can delete these cross terms. So, what it means is, let us say we have two weights, we can say that the change in error, if we let us say we have two weights, weight 1 and weight 2. So, if we do two experiments where we change W1, or if we just prune W1 and then take the accuracy, and then if we prune W2 and then take the accuracy, those two are independent. Okay. So, the change in error caused by deleting one filter is independent of others, right. And then we can also assume the network has already been converged. So, we can safely delete this first terms. Remember, I mean, whenever our DNN is trained well, our objective or the objective of DNN training is to make sure that delta ui over delta ei is 0, right. So, that is why we can say that gi is 0 that means the DNN is trained well. So that term can go away. Now with that, now we can also say that the cost function is nearly quadratic. The last term can also be deleted. The last term is like higher order term where the order is 2 or more, sorry, order is 3 or more, right. Now as you can see that we just have only one parameter or only one expression left for delta E. Now the parameter which with the smallest delta, the parameter which has the smallest delta E will be removed. So this particular term can be computed mathematically for all the neurons or for all the weights, right. If we know the input, then we can compute that highlighted part mathematically. So and that highlighted part is basically the change in error if we change weight I by delta ui. Okay. Now if the error is less, if the change in error is less, that means the weight can be removed, right. I mean if the change in error delta E is less, even if we are change, if the change in error if the change in error delta E is less, even if we are changing delta ui, that means ui has almost no effect on the error, correct. So that means we can safely remove this ui. That is one technique. Then again there are technique which is which implements like activation based pruning. So the zero activation neurons are redundant and can be removed without affecting the overall accuracy of the network. So let us say we observe that for many input, some activations are always 0, some activations which are produced by some particular weights are always 0. That means we actually do not need the weights, even if there are even if the weight values are high, maybe for some reason the input activation to the weights are always near 0. So the output is also near 0, right. So this particular technique can be done through computing average percentage of 0 activation, which is used to measure the importance of filters. Now the filter with higher APOZ can be removed. So let us say we have 3 channels and then we have batch of 2, I mean 2 input, right. Now when I say 3 channel, that means we have 3 output channels. So remember, if we have 3 output channel, that corresponds to 3 filters in the convolutional process or in the convolutional layer, right. Now as you can see that we are computing the average percentage of zeros. In channel 0 we can see that there are 11 zeros. So for an example, in channel 0 for batch 1 we have 1, 2, 3, 4, 5 zeros, and in batch 2 we have 1, 2, 3, 4, 5, 6 zeros, right. So total 11 zeros in channel 1, correct. Now similarly in channel 0, in the first in 0th channel, in the channel 1 we have 12 zeros, in channel 2 we have 14 zeros. Now as you can see there are more number of zeros in channel 2, so we can prune, so we do not need channel 2, and channel 2 is coming from filter 2 of the convolutional layer. So we can remove this filter 2, that is the structured pruning, right. So computing average percentage of 0 activation is one of the simpler technique to perform the pruning. Now there is a technique called scaling based pruning. Now the aim of this scaling based pruning is to find the important and redundant layers while training the network itself, right. Now for channel pruning of CNN, each channel can be associated with a scaling factor which are tunable parameters. So for an example, let us say we have this C1, C2, C13, C till CI1, CI12 till CI1, CIN as the channel, right, or as the probably layer. Sorry, not channel. This is the ith convolutional layer, and these are the channels. Yes. Now let us say while training, we associate one scaling factor alpha I to each of the channel, and these alpha i's are, let us say not let us say, these alpha i's are trainable parameters, right. So it will be like whatever computation is happening in CI1, that will be multiplied by alpha I1, and then whatever computation is happening in CI2, that will be multiplied by alpha I2, and so on and so forth. Now let us say the train values, after we train the network with this alpha I1, alpha I2, etc., the train values of this CI1, CI2 usually remains in the same distribution, let us say -1 to 1, right. Now that means if some channel has higher alpha I1, that denotes that the channel has more importance. If some channel has lower alpha I, that means the channel has lower importance, correct. Now if that is the case, we can safely say the channel which has lower scaling factor, we can remove the channel, right. So that is the philosophy behind this scaling based pruning. In this particular case, you can see that some channel had the scaling factor of 0.001, 0.003, etc. Those channels have been removed. So that is the scaling based pruning. But then the problem is there are ResNet like network where there are residual connection or the skip connections, right. Now the skip connections contain coupled channel. Now coupled channel means there are two channel which are dependent on each other. So two channels or two layers which are dependent on each other. That means it is very difficult to find one scale factor which is common between the coupled channel. So that is why the channel of multiple layers are coupled in the case of ResNet, and they need to be pruned simultaneously. As I was saying, that it is challenging to determine one particular scale for both the channels, and that is why prior pruning algorithms keep pruning the coupled channel due to its complexity. But then if we skip those coupled channels from pruning, that will lead to lower benefit in execution time. For an example, ResNet, let's take ResNet. Almost all its channels are coupled channel, right. So ResNet has multiple blocks, if you remember, and then in each block there are skip connection. Whenever we have a skip connection, that means it will give us a coupled channel, right. If we skip pruning for all the coupled channels, then we may end up not pruning anything. So that will lead to lower benefit in execution time. Again, you can see these references to know more about scaling based pruning, as well as there are some work which tries to perform the coupled or perform the scaling based pruning for coupled channel also. Now so far what I have seen, what we have discussed, or what we are going to discuss is a recipe for neural network pruning. So first we need to select the pruning granularity, like whether we want to do element wise pruning, vector wise pruning, or the filter wise pruning, and then we have to select the parameters to prune. We have seen the derivative based selection, average, percentage of zero based selection, then scaling based selection. That is the different technique. Those are the different techniques to select the parameters to prune, and then finally we remove the parameter. After that, usually fine tuning is done to recover some of the lost accuracy, and then this process happens in an iterative fashion. So we need to repeat the process. Now the question is this the only procedure for pruning the neural network model? Of course not, otherwise the lecture would have been finished here only, right. So there are some pruning technique which is known as dynamic pruning. So far whatever we discussed is called static pruning. Now in static pruning, we permanently remove the network parameter in which in general cannot be recovered. So let us say we train a model and then we find the importance of some parameter through, let us say, derivative based or scaling based or whatever, and then we just remove the parameters for good, right. So we cannot recover those parameters. So that is static pruning, or that happens in static pruning. Now it may lead to decrease in model capacity, leading to non-recoverable accuracy, right. So moreover, remember, whenever we are pruning, then so if you remember the mathematical formulation of pruning, we discussed that during pruning we try to keep the accuracy intact, or we try to take the prune network which has maximum accuracy. When we say maximum accuracy, that is on a specific data set, right. But in practice we might get one input which is not from the data set, like in real time. Let us say we trained a network with let us say ImageNet data set. Okay. Now ImageNet data set has images of different animals, but let us say in practice it encounters, let us say the ImageNet, we train some VGG with ImageNet data set, we deploy the VGG in the phone, and then the uh, job of the application of the phone is to detect and tell which animal it is. Now, let us say it encountered some animal which was not trained with, let us say unicorn, mermaid, something, right. Then in that case the application will say that okay, I do not know this animal, right. The main reason, the main problem is probably it would have been known, it would have known the animal, but then we already pruned, and the prune network is like tightly coupled with the data set. So, that is why I am saying static pruning does not take account the current input or the input which may come in real time. Now, instead there is a technique called, or there are techniques called dynamic pruning, which determines in runtime like which parameters, filter, connections, layers will be skipped in the forward pass, and the network is pruned more for images which are easier to predict. Maybe some image, let us say football or a soccer ball, right, that can be predicted very easily. So, maybe for that we may be able to prune the network heavily, right, but at the same time let us say some complex image, let us say Picasso's drawing or something like that, we need to have like more complex network, and for that maybe the pruning requirement should be very less, right. So, basically what I am trying to say, at real time we may encounter different images, and for those different images the pruning requirement should be different, and dynamic pruning actually takes care of that. So, since the ability of the network is fully preserved in the dynamic pruning, the original network is there, but then depending on the network, or not the network, but depending on the input image, different part of the network is not activated or the forward pass is not done. That is the dynamic pruning. Let us take one example. Now, of course, the biggest question is how to determine which part of the network will not be required for the image, right. So, in this particular example there is dynamic pruning or runtime pruning, which is consisting of two sub network. One is CNN backbone, like the regular convolutional neural network, and then there is a decision network. In this particular case, the decision network is nothing but one recurrent neural network. So, there is a mask variable which can be used to denote the filters that will be used in the forward pass for the current iteration. So, what it does is, let us say we have this feature maps. Now, the feature maps, yes, these feature maps are used for next layer of CNN or whatever, but at the same time these feature maps are also passed to this RNN encoder, and then it RNN computes something which is passed to the decoder, and it says which layers to be pruned. So, specifically it says, it gives a vector of or string of binary values, where 1 means that particular channel can be pruned, or and 0 means the particular channel should not be pruned, or vice versa, something like that. So, the bottom line is, it takes the feature maps. Yes, the feature maps are used for different convolutional network. At the same time, the feature maps are also used to determine whether some channel or which channel needs to be pruned. That is that's the backbone network, or the decision network. So, not the backbone network, CNN network is the backbone network. The decision network is RNN in this case, which is determining which channels to keep and which channels to prune, right. So, that is a dynamic pruning. Now, yeah, I mean we already discussed in this slide that based on the feature map, the decision network dynamically prune the kernels for the ith layer in the backbone network. So, as you can see in this particular case, I mean this was pruned, these 3 were pruned, these 2 were pruned, and so on and so forth. So, as you can see, the whole capability, the entire capability of the original CNN is kept. So, if we are deploying on the edge device, the entire network is deployed on the edge device, but then some of the channels are pruned, right. During forward pass, some of the channels are not even used. So, we will obtain some benefit in the execution time, right. At the same time, since we are enabling different prune channel for different images, we also are kind of preserving the accuracy. Like for some image, it might be the case that we can sustain like heavy pruning, so the inference latency will be very low, and accuracy will be preserved. On the other hand, there can be some complex images where most of the network may be untouched, may be unpruned, but still the accuracy will be intact, accuracy will be higher. So, for all images the accuracy is higher. Now, we are opportunistically pruning the network, so that for some images the inference latency is low, some images inference latency might be higher, right. Now, if we compare static pruning versus dynamic pruning, the static pruning is performed offline prior to the inference, while dynamic pruning is performed at the runtime, which we discussed. Dynamic pruning requires no fine tuning after pruning. So, remember we are just pruning at real time and then we are performing the inference. So, there is no concept of fine tuning in dynamic pruning, and dynamic pruning may result in higher overhead, which is an important consideration compared to static pruning, because remember in dynamic pruning there is a decision network. In the previous example our RNN was a decision network. So, we have to make sure that the decision network does not impose a high overhead, so that whatever latency benefit we are obtaining from pruning is gone, right. Now, with that let us discuss something called lottery ticket hypothesis. So, this is a very famous pruning technique. You can go and read the paper to know more. In this lecture I will just give you a brief overview of lottery ticket hypothesis. The lottery ticket hypothesis asks the question whether we can train a sparse network which is a subset of some dense network from scratch and achieve the same level of accuracy. But then question is how to identify the sparse network. So, iterative magnitude pruning is one such way, but then so let us say we have a dense network which is the initial model, then we train the model, we converge the model, and then we prune. Now, the prune model, even if we retrain the prune model, there are cases where we are probably unable to recover the accuracy. This is the usual flow, right. This is the usual flow. We train a dense model, then converge the model, we prune. After pruning we can do fine tuning, but in many cases we will see that even after fine tuning we are unable to recover the accuracy. Now, instead the lottery ticket hypothesis says it does not change the flow much. Again we have this initial model, after training the model is converged, then we prune to get a prune model. After we have this prune model, they are saying we should reinitialize to this original values. So, remember initial model, all the weights in the initial model were initialized with a random weight, right, and then it got trained. So, after pruning, instead of retraining on the same pruned model, we need to reinitialize to the original values, and the intuition is from that initial weights there is already a path to the train, to the converged model which has already been learned. So, if we reinitialize the pruned model weights to the original values, then if we perform the retraining, it is seen that similar accuracy performance is obtained, right. That is the lottery ticket hypothesis. So, again here the initial model is always a dense model, and then they are trying to see whether a subset of the dense model is good. I mean same dense model can be instantiated for different application. After that they are trying to see whether the same technique, the same flow is applicable for all the applications or not. So, the main thing, the main difference between lottery ticket hypothesis and the prior work is this reinitializing to the original values. So, instead of fine tuning from scratch, or not scratch, sorry, instead of retraining directly from the prune model, if we retrain by reinitializing the original values, it has been seen that the similar accuracy performance is achieved compared to this initial model. Whenever we say similar performance, of course, the accuracy performance is compared to with the initial model. Again, please go through the paper yourself, and then you will see they have a rigorous proof through which they argue that it is theoretically, I mean they theoretically prove that it is better to reinitialize the weights in prune model to the original values before we perform the retraining. Okay. So, that is it for this lecture. Thank you very much. We will see you in the next lecture.